Good morning students. In today's session we are going to discuss about molecular orbital theory. Why this molecular orbital theory has been put forth? We have already valence bond theory. Because of the drawbacks of valence bond theory, this new theory called molecular orbital theory have been put forth. What are the drawbacks of valence bond theory then? In valence bond theory, the magnetic nature of the molecule could not be explained, and as well as the stability of the molecule could not be explained by the valence bond theory. These few drawbacks of the valence bond theory has been overcome by this molecular orbital theory. So, in this session we are going to discuss about the important topic, that is molecular orbital theory. According to this molecular orbital theory, the two atomic orbitals combine to give two new orbitals. These two new orbitals are known as molecular orbitals. Whereas in valence bond theory, when atomic orbitals combine, the electron sharing will take place as well as covalent bond has been formed. But in this molecular orbital theory, the two atomic orbitals will combine with each other to form two new orbitals which are known as molecular orbitals. In these molecular orbitals, the electron sharing will take place and these molecular orbitals will involve in the bond formation. Whereas in VBT, these atomic orbitals will involve in the bond formation. But according to this molecular orbital theory, these two molecular orbitals will involve in the bond formation. This is about the molecular orbital theory, how the molecular orbital will going to form from atomic orbitals. So, which atomic orbital will form molecular orbital? The atomic orbitals which are of same energy. The atomic orbitals which are of same energy means if the atomic orbital present in 1s will combine with the atomic orbital of 1s itself. It can't be combined with the atomic orbital of 2s because of different energy. So, the atomic orbitals of the same energy and same shape can combine to give the molecular orbital. What do you mean by same shape? Means you can observe here, this is the shape of the s orbital. From this you can know that the s orbital can combine with s orbital itself. The s orbital cannot combine with the p orbital because you can observe here the shape of the p orbital is dumbbell and the shape of the s orbital is spherical. So, according to this theory, the atomic orbital possessing the same shape can combine with each other, whereas here there are different shapes. So, the atomic orbitals of same energy and same shape can combine to form molecular orbitals. But when you observe the valence bond theory, there in the hybridization, the two different atomic orbitals could combine, that is s and p atomic orbitals will intermix with each other to form hybridization. But in molecular orbital, the atomic orbitals of same energy and same shape could combine to form molecular orbitals. How many molecular orbitals will going to form? ಎಷ್ಟು atomic orbitals combine ಆಗುತ್ತೋ ಅಷ್ಟು molecular orbitals form ಆಗುತ್ತೆ. And you can observe here the two atomic orbitals have been combining to give two molecular orbitals. These two molecular orbitals are known as, the first one is known as bonding molecular orbital and other is known as anti-bonding molecular orbital. So, based on the wave mechanics, we have been classified the molecular orbital into bonding molecular orbital and anti-bonding molecular orbital. How this bonding molecular orbital has been formed? By the addition of two wave function, we will get the bonding molecular orbital, whereas by the subtraction of two wave functions, we are going to get anti-bonding molecular orbital. That is, So you can observe here the crust of two wave function are on the same side, that is constructive interference. That means the bonding molecular orbital has been formed. You can observe here in anti-bonding molecular orbital, the crust of one wave function is opposite to the crust of other wave function. That means the two wave functions are nullifying with each other, that is destructive interference. Therefore, what do you mean by bonding molecular orbital? The addition of two wave functions will give you bonding. The subtraction of two wave function will give you the anti-bonding molecular orbital. We can represent this bonding molecular orbital as sigma pi delta, whereas we can represent this anti-bonding molecular orbital as sigma star, pi star and delta star. This is how we are going to represent bonding molecular orbital and anti-bonding molecular orbital. Usually the anti-bonding molecular orbitals are represented by the stars, and the electron filling in these bonding molecular orbitals and anti-bonding molecular orbitals takes place according to the Pauli's exclusion principle, Aufbau principle and as well as Hund's rule of maximum multiplicity. This is what about the molecular orbital theory. Now let us consider the energy level diagram for this molecular orbital theory. So this would be the energy level diagram for the molecules containing 14 electrons or less than 14 electrons. This is called molecular orbital energy level diagram. The energy level diagram has been formed in the increasing order of the energy. So firstly, 1s atomic orbitals, the atomic orbitals have been combined to form two molecular orbitals. That is, one is bonding molecular orbital and other is anti-bonding molecular orbital, that is sigma 1s and sigma star 1s. Usually always bonding molecular orbital have lesser energy compared to anti-bonding molecular orbitals. That's why the bonding molecular orbital has been represented in the lower energy and anti-bonding molecular orbital has been represented in the higher energy. As bonding molecular orbital is possessing the lower energy, it has maximum stability. The bonding molecular orbital has maximum stability, whereas anti-bonding molecular orbital least stable. Therefore, this is about the molecular orbitals, that is bonding and anti-bonding orbital. That is 1s atomic orbital combined with other 1s atomic orbital to form sigma 1s, that is bonding molecular orbital, and sigma star 1s, that is anti-bonding molecular orbital. Why have written sigma? As we know, always s atomic orbitals combine to give only sigma bond. They will never form pi bond. Therefore, ss orbital combine to give sigma 1s and sigma star 1s. Sigma 1s represents bonding molecular orbital and sigma star 1s represents anti-bonding molecular orbital. Similarly, the next level is 2s atomic orbitals. The 2s atomic orbital of one atom will combine with the 2s atomic orbital of other atom to give two molecular orbitals. Always s orbital will form sigma bond. The two molecular orbital would be sigma 2s, that is bonding molecular orbital, and sigma star 2s, that will be anti-bonding molecular orbital. The next level is p orbital. We are considering the p orbital, that is 3 p orbitals have been formed, px, py, pz. Usually we assume that pz orbital will always form sigma bond by axial overlapping, whereas px and py will usually form pi bond by sideways overlapping. Here, firstly, the px and py orbitals overlap in a sideways manner with other px and py orbitals to form pi px and pi py bonding molecular orbital, as well as pi star 2px and pi star 2py as anti-bonding molecular orbital. Secondly, the pz atomic orbital of one atom will overlap with the pz atomic orbital of other atom to give two molecular orbitals, that is sigma 2pz bonding molecular orbital and sigma star 2pz anti-bonding molecular orbital. This is how we are writing the molecular orbital diagram, that is energy level diagram, in the increasing order. First one is, then 2s, then px, py, pz orbitals. This is how the energy level diagram for the molecules having 14 electrons or less than 14 electrons. So, the electronic configuration for this molecular orbital diagram is firstly sigma 1s, which is lower energy, then sigma star 1s, that is anti-bonding, nextly sigma 2s and sigma star 2s, finally pi 2px, pi 2py. These two have same energy. Pi 2px and pi 2py will have same energy. Then sigma 2pz, then pi star 2px and pi star 2py, which will have same energy. Finally sigma star 2pz. This is how we are going to write the electronic configuration in the increasing order, as well as the electrons have been filled in this orbital in the increasing order itself. Now let us consider the first molecule as hydrogen molecule. We know that the hydrogen molecule is the combination of two hydrogen atoms. The atomic orbital of these two hydrogen atoms will overlap with each other to form two molecular orbitals. These molecular orbitals involved in the bond formation. As we know, the atomic number of hydrogen is 1. One hydrogen ge one atomic number. There are two hydrogen atoms. Therefore, how many number of electron has been present? 2 electrons. Total number of electron 2. So, firstly, we should accommodate the 2 electron in this electronic configuration. As we know, each orbital can have maximum of 2 electrons. So, the electronic configuration would be sigma 1s2. ಇರೋ 2 electrons ಇದಕ್ಕೆ ಹಾಕಿದ್ವಿ, ರೈಟ್? ಇನ್ನು ಮಿಕ್ಕಿದ ಎಲೆಕ್ಟ್ರಾನ್ ಇದೆಯಾ? ಇಲ್ಲ ಅಂದರೆ ಮುಂದಕ್ಕೆ ಹೋಗೋಂಗಿಲ್ಲ. Therefore, the 2 electrons has been accommodated in sigma 1s electron. Therefore, the energy level diagram for this molecule would be, as the electron has been accommodated in the sigma 1s itself, we should consider only this much of the molecular orbital diagram, that is only the sigma 1s and sigma star 1s orbital diagram. So, this is the atomic orbital. Each hydrogen atom contains 1 electron. Each hydrogen atom contains 1 electron. These hydrogen atoms will combine with each other to form like this, sigma 1s and sigma star 1s. The electrons will go to the lower energy orbital, that is bonding molecular orbital, which is sigma 1s orbital. This is what the energy level diagram for hydrogen molecule. Nextly, we should find the bond order for this hydrogen molecule. Firstly, what do you mean by bond order? It is nothing but the number of bonds present in between the two atoms is known as bond order. ಎಷ್ಟು ಬಾಂಡ್ಸ್ ಇದೆ ಅಂತ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡೋದನ್ನೇ ನಾವು ಬಾಂಡ್ ಆರ್ಡರ್ ಅಂತ ಕರಿತೀವಿ. ಸೊ ದ ಫಾರ್ಮುಲಾ ಇನ್ ಆರ್ಡರ್ ಟು ಕ್ಯಾಲ್ಕುಲೇಟ್ ದಿ ಬಾಂಡ್ ಆರ್ಡರ್ ಇಸ್, ಇಟ್ ಈಸ್ ಈಕ್ವಲ್ ಟು half of the number of electron present in bonding molecular orbital minus number of electron present in anti-bonding molecular orbital. So, in this hydrogen molecule, the 2 electron has been present in the bonding molecular orbital. Therefore, which is equal to half into 2 minus the number of electrons in anti-bonding is 0. Therefore, 2 minus 0, which will be equal to 1. If the bond order is 1, that means between 2 hydrogen atoms there is only one bond present. That is, like this the hydrogen molecule exists. That is, one bond is present between the 2 hydrogen atoms. And nextly, the magnetic nature of this hydrogen molecule. We know that if the electron has been paired in an orbital, that is diamagnetic. If the electrons have been unpaired, then it is paramagnetic in nature. You can observe here the s orbital is fully filled, that is each orbital contain only maximum of 2 electrons. Therefore, 2 electron has already been filled. Therefore, the magnetic nature of this hydrogen molecule is diamagnetic. As there is no unpaired electron in this molecule, the magnetic nature is diamagnetic nature. So, this is how we are going to calculate the bond order and magnetic property of a given molecule by using the molecular orbital diagram, that is energy level diagram. Now, let us consider the next example as helium molecule. This helium molecule is made up of 2 helium atoms. As we know, each helium atom contains 2 electrons. Therefore, number of electrons would be 4 electrons. The number of electrons would be 4 electrons. So, the accommodation sigma 1s 2, sigma star 1s 2. 4 electrons ಮುಗಿತು, ಮುಂದಕ್ಕೆ ಹೋಗಬೇಕಾ? ಹೋಗೋ ಅವಶ್ಯಕತೆ ಇಲ್ಲ. The 4 electrons has been accommodated. You can observe here the molecular orbital diagram for this helium molecule is constructed only for 1s and sigma 1s star. ಮುಂದಕ್ಕೆ ಬರ್ಕೋಬೇಕಾ sigma 2s ಬೇಡ, ಅಲ್ಲಿರೋದೇ electrons fill ಆಗಿರೋದೇ sigma 1s star ವರೆಗೆ. So the energy level diagram is constructed to this sigma 1s. We no need to take this sigma 2s. Therefore, this would be the energy level diagram where each helium atom consists of 2 electrons in their atomic orbital. They will combine to give 2 electron in sigma 1s and 2 electron in sigma star 1s orbital. This is the energy level diagram. Nextly, we should calculate the bond order. We know that the bond order is equal to half into number of electrons in bonding molecular orbital minus number of electrons in anti-bonding orbital. So, you can calculate here the number of electrons in bonding is 2 and the number of electrons in anti-bonding is 2. Therefore, the bond order would be 0. If the bond order is 0, that means there is no bond exists between helium molecule. If there is no bond means the helium molecule itself will not exist. There is no existence of this helium molecule. Finally, the magnetic nature. You can observe here both the orbitals, that is bonding and anti-bonding orbitals, are completely filled. Therefore, the magnetic property would be diamagnetic in nature. Now, let us move on to the another example, lithium molecule. So, lithium molecule is the combination of 2 lithium atoms. We know that one lithium atom contains 3 electrons. Therefore, 2 lithium atoms contain 6 electrons. Therefore, the number of electrons present in the lithium molecule would be 6 electrons. Therefore, accommodation of 6 electrons by this electronic configuration would be sigma 1s2, sigma star 1s2, sigma 2s2. ಇಲ್ಲಿಗೆ ಕನ್ಸ್ಟ್ರಕ್ಟ್ ಆಗುತ್ತಲ್ವಾ, ಮುಂದಕ್ಕೆ ಹೋಗ್ಲಿಕ್ಕೆ ಆಗಲ್ಲ. ಯಾಕೆ? ಇರೋದೇ 6 ಎಲೆಕ್ಟ್ರಾನು ಈ ಥರ ಫಿಲ್ ಮಾಡಿ. ದೆನ್ ದಿ ಎನರ್ಜಿ ಲೆವೆಲ್ ಡಯಾಗ್ರಾಮ್ ಫಾರ್ ದಿಸ್ ಲಿಥಿಯಂ ಮಾಲಿಕ್ಯೂಲ್ ವುಡ್ ಬಿ ಆಸ್ 2s ಆರ್ಬಿಟಲ್ ಈಸ್ ಇನ್ವಾಲ್ವಿಂಗ್, ವಿ ಶುಡ್ ರೈಟ್ ದಿ ಮಾಲಿಕ್ಯುಲರ್ ಆರ್ಬಿಟಲ್ ಅಪ್ ಟು ದಿಸ್. ಇಲ್ಲಿವರೆಗೂ ಮಾಲಿಕ್ಯುಲರ್ ಆರ್ಬಿಟಲ್ ಡಯಾಗ್ರಾಮ್ನ ಬರ್ಕೋಬೇಕು. ಯಾಕೆ? ಎಲೆಕ್ಟ್ರಾನು 2s ಆರ್ಬಿಟಲ್ಗೂ ಹೋಗಿರೋದ್ರಿಂದ ನಾವು ಇಲ್ಲಿವರೆಗೂ ಮಾಲಿಕ್ಯುಲರ್ ಆರ್ಬಿಟಲ್ನ ತಗೋಬೇಕು. ಸೊ ದಿಸ್ ವುಡ್ ಬಿ ದಿ ಮಾಲಿಕ್ಯುಲರ್ ಆರ್ಬಿಟಲ್ ಡಯಾಗ್ರಾಮ್ ಫಾರ್ lithium molecule. The 1s orbital of each lithium atom contain 2 electron, whereas 2s atomic orbital of each lithium atom contain 1 electron. So it will combine to give. So this will be the molecular orbital diagram for the lithium molecule. From this we can calculate the bond order. The bond order would be the number of electron in bonding orbital would be 4 electrons. And the number of electrons in anti-bonding 2. Therefore, 4 minus 2 which is equal to 2. The bond order is 1. The bond order is 1 means the lithium molecule exists like this. There is one bond in between 2 lithium atoms, and we can observe the magnetic property as diamagnetic. As there is no unpaired electron, the magnetic property is diamagnetic. This is about the lithium molecule. Now, let us consider the carbon molecule. Now, let us consider the carbon molecule. Each carbon contains 6 electrons. Therefore, total number of electrons in carbon molecule would be 12 electrons. The filling of 12 electrons follows Aufbau principle, Hund's rule and Pauli's exclusion principle. Therefore, sigma 1s2, sigma star 1s2, sigma 2s, sigma star 2s. ಎಷ್ಟು electrons fill ಆಯಿತು? 8 electrons fill ಆಯಿತು. Next what we should do? We should add 1 electron to this pi 2px and 1 electron to this pi 2py. ಎಷ್ಟಾಯಿತು? 10 electron ಆಯಿತು. ಇನ್ನೂ 2 electron ಇದೆ ಅಲ್ವಾ? Then addition of 1 electron to this and addition of 1 electron to this. ಈ ಥರ ಆ್ಯಡ್ ಮಾಡಬೇಕು. ಡೈರೆಕ್ಟಾಗಿ ಇದಕ್ಕೆ ಆ್ಯಡ್ ಮಾಡೋ ಹಾಗಿಲ್ಲ. ಇದು ಎರಡಕ್ಕೂ ಫಸ್ಟು ಒಂದೊಂದು ಎಲೆಕ್ಟ್ರಾನ್ ಕೊಡಬೇಕು, ಎರಡು ಒಂದೊಂದು ಎಲೆಕ್ಟ್ರಾನ್ ತೊಗೊಂಡ ಮೇಲೆ ಇವೆರಡಕ್ಕೂ ನೆಕ್ಸ್ಟ್ ಒಂದೊಂದು ಎಲೆಕ್ಟ್ರಾನ್ ಹಾಕಬೇಕು. This is how the electron filling takes place. Totally 12 electrons has been accommodated. The energy level diagram for this carbon molecule would be as it is, including the pi orbital also, the p orbital also. We should consider this molecular orbital diagram for the carbon molecule. These are the atomic orbitals of the carbon atom. 1s atomic orbital of carbon atom contain 2 electrons, and 2s atomic orbital of carbon atom contain 2 electrons, and 2p atomic orbital contains 2 electrons. Therefore, after mixing with each other, the electron sharing takes place like this. This is how the electron sharing takes place in a carbon molecule. This is the molecular orbital diagram for the carbon molecule. From this, we should calculate the bond order, which is equal to half into number of electrons in bonding. 1, 2, 3, 4. 4 bonding molecular orbitals, that means 8 electrons, minus number of electrons in antibonding 2, 4, which would be equal to 2. That means in between two carbon atoms, the 2 bond has been existed. In between two carbon atom, the 2 bonds has been existed. One would be the sigma bond and other would be the pi bond. This is about the bond order of the carbon molecule. Nextly, the magnetic nature. You can observe here all the orbitals have been completely filled. Here also the pi orbital has 2 electron. This pi orbital also has 2 electron. Therefore, this orbital has been completely filled. Therefore, the magnetic nature would be diamagnetic in nature. This is about the carbon molecule. Now, let us consider the another molecule as nitrogen molecule. Let us consider the nitrogen molecule. We know that the nitrogen molecule is made up of nitrogen atoms. The one nitrogen atom contains 7 electrons, therefore 2 nitrogen atom contain 14 electrons. The accommodation of these 14 electrons according to the Hund's rule, Pauli's and Aufbau principle. Therefore, sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px ಗೆ 1, pi 2py ಗೆ 1. ಎಷ್ಟು ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ಆಯಿತು? ಟೋಟಲಿ 10 ಆಯಿತು. ಇನ್ನು 4 ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ಅಕಾಮಡೇಟ್ ಮಾಡಬೇಕು. +1, ಸಿಮಿಲರ್ಲಿ +1. ಈಗೇನಾಯಿತು? 12 ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ಆಯಿತು. ಇನ್ನೂ 2 ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ಇದೆ. ಸಿಗ್ಮಾ 2pz 2. This is how the electrons accommodation takes place in the molecular orbitals. Now, from this we should write the molecular orbital diagram. You can observe here the electron, last electron enters into the sigma 2pz orbital. Therefore, we should consider the whole molecular orbital diagram. You can observe here 1s orbital of nitrogen is completely filled, 2s atomic orbital of nitrogen is completely filled, and 2p atomic orbitals are half filled. Similarly, in this way, these are the atomic orbitals of another nitrogen atom. Both of combining together to give the molecular orbitals. So, one electron in 1s and other electron in 1s combine to form sigma 1s. Similarly, other 2 electrons combine to form sigma star 1s. Similarly, in this, this is how the electron sharing takes place in the nitrogen molecule. From this, we are going to calculate the bond order, which will be equal to the number of electrons in bonding orbital 2, 4, 6, 8, 10, minus number of electrons in anti-bonding orbital 2, 4, which would be equal to 3. That means the 3 bonds exist between 2 nitrogen atoms. One is sigma bond and other 2 is pi bond. Finally, the magnetic nature, you can observe here all the orbitals are completely filled, hence it is a diamagnetic in nature. This is about the electronic configuration, bond order, molecular orbital diagram and magnetic nature of nitrogen molecule. These are few examples, few molecules which contains 14 electrons or less than 14 electrons. Now, let us consider the molecular orbital diagram and the electronic configuration for the molecules which contains more than 14 electrons. This will be the molecular orbital diagram and electronic configuration for the molecules containing more than 14 electrons. What would be the difference? The only difference is the first comes will be the sigma 2pz. First molecular orbital barutte sigma 2pz. Then pi 2px and pi 2py. You can observe in the electronic configuration, the firstly sigma 2pz orbital should be filled, then pi 2px and pi 2py orbital should be filled. Ade 14 electrons alli idu ulta agittu. First pi 2px pi 2py fill agಬೇಕಾಗಿತ್ತು, ಆಮೇಲೆ sigma 2pz fill agಬೇಕಾಗಿತ್ತು. But for the molecules containing more than 14 electrons, ಯಾವುದು first fill ಆಗಬೇಕು? sigma 2pz fill ಆಗಬೇಕು, ಆಮೇಲೆ pi 2px pi 2py fill ಆಗಬೇಕು. This is the electronic configuration and molecular orbital diagram for the molecules containing more than 14 electrons. So, let us consider the first example as oxygen molecule. Each oxygen atom contains 8 electrons. Therefore, 2 oxygen atom, therefore number of electrons would be 16 electrons. Therefore, the number of electrons would be 16 electrons. These 16 electrons should be accommodated in these molecular orbitals in the increasing order of the energy, that is sigma 1s2, sigma star 1s2, sigma 2s, sigma star 2s, sigma 2pz2. How many electrons has been accommodated? 2, 4, 6, 8, 10. ಉಳ್ಕೊಂಡಿರೋದು ಇನ್ನೆಷ್ಟು? 6 electrons. Next pi 2px1, pi 2py1. Again pi 2px1, pi 2py1. How many electrons has been accommodated? 14 electrons has been accommodated. Remaining 2 electrons, that is pi star 2px1, pi star 2py1. This is how the electrons have been accommodated in the various molecular orbitals. And the molecular orbital diagram for the oxygen molecule would be like this. ಯಾಕೆ electrons ಎಲ್ಲಿವರೆಗೂ accommodate ಆಗಿದೆ? pi star ವರೆಗೂ accommodate ಆಗಿದೆ. Therefore, we should consider the whole molecular orbital diagram for this oxygen molecule. So, this would be the molecular orbital diagram for oxygen molecule. You can observe here the 1s orbital of the one oxygen atom contain 2 electron, 2s orbital contain 2 electron, and 2p orbital contain 4 electrons, 2px2, 2py1, 2pz1. Similarly, these are the atomic orbitals of the other oxygen atom. When 2 atomic orbitals combine, they will give bonding and anti-bonding molecular orbitals, and electron sharing takes place in this manner. So, when you are going to calculate the bond order would be half into number of electrons in bonding 2, 4, 6, 8, 10. 10 electrons in bonding minus number of electrons in anti-bonding 2, 4, 5, 6, which would be equal to 2. That means there are 2 bonds in between 2 oxygen atoms. That is, one is sigma bond and other is pi bond. This is the bond order of the oxygen molecule. Now we should calculate the magnetic nature of the oxygen molecule. You can observe here the last valence shell orbital, molecular orbital, contains 1 electron. In order for the complete orbitals, we need 2 electrons. Adre allirodu eshtu? One electron. That means it has been unpaired electron. That means the magnetic nature would be paramagnetic in nature. The oxygen molecule is paramagnetic in nature. This is about the oxygen molecule, its molecular orbital configuration, its bond order and molecular orbital diagram. Finally, the magnetic nature of oxygen molecule. Now, let us consider O2 minus, ಅಂದರೆ ಒಂದು ಅಡಿಷನಲ್ ಆಗಿ ಒಂದು ಎಲೆಕ್ಟ್ರಾನ್ ಆ್ಯಡ್ ಆಗಿದೆ ಅಂತ ಅರ್ಥ. Therefore, the electronic configuration would be ಲಾಸ್ಟಲ್ಲಿ ಏನಾಗುತ್ತೆ, ಒಂದು ಎಲೆಕ್ಟ್ರಾನು pi star 2px ಆ್ಯಡ್ ಆಗುತ್ತೆ. pi star 2px ಆ್ಯಡ್ ಆದ ತಕ್ಷಣ ಬಾಂಡ್ ಆರ್ಡರ್ ಏನಾಗುತ್ತೆ, ಇಲ್ಲಿ 6 ಇದ್ದಿದ್ದು ಏನಾಗುತ್ತೆ 7 ಆಗುತ್ತೆ. ಆಗ ಬಾಂಡ್ ಆರ್ಡರ್ ಏನಾಗುತ್ತೆ 10 minus 7 3. 3/2 means 1.5. Similarly, when you consider O2 plus, O2 ಪ್ಲಸ್ ಅಂತ ಕನ್ಸಿಡರ್ ಮಾಡಿದರೆ ಒಂದು ಎಲೆಕ್ಟ್ರಾನ್ನ ರಿಮೂವ್ ಮಾಡಿದ್ದೀವಿ ಅಂತ ಅರ್ಥ. ಎಲ್ಲಿಂದ ರಿಮೂವ್ ಮಾಡಬೇಕು? pi star 2p ಇಂದ ರಿಮೂವ್ ಮಾಡಬೇಕು. So this will be the original electronic configuration for the oxygen molecule. You can observe here the removal of one electron takes place from this molecule. ಆಗ ಏನಾಗುತ್ತೆ? ಆಂಟಿ ಬಾಂಡಿಂಗ್ ಅಲ್ಲಿ ಒಂದು ಎಲೆಕ್ಟ್ರಾನ್ ಕಡಿಮೆ ಆಗುತ್ತೆ. Therefore bond order would be 2.5 for the O2 plus molecule. When you observe O2, O2 minus and O2 plus, the bond order for oxygen would be 2 and bond order for O2 minus is 1.5 and bond order for O2 plus is 2.5. You can observe here the increase in the bond order gives the stability of the molecule. If the molecule is possessing more bond order means the molecule is more stable. Here in these three molecules O2 and O2 minus and O2 plus, you can observe here the O2 plus is possessing 2.5 bond order. Therefore this molecule is more stable than O2, which is more stable than O2 minus. Always the bond order is directly proportional to the stability. Greater the bond order, greater would be the stability. Therefore in these three molecules the O2 plus has maximum stability because the bond order is greater in the O2 plus compared to O2 than O2 minus. This is about the bond order related to stability. Greater the bond order means greater would be the stability. This is about molecular orbital theory concept. The energy level diagram for the molecules possessing less than 14 electrons and more than 14 electrons and respective electronic configuration and how to calculate the bond order, and finally the bond order related to the stability of the molecules.